Right, sorry, I was cut off just now by the 5 minutes constraint of the video recording. Uh, yeah, in the previous video, I was saying that if we take the differentiation of the linear momentum, then we and equate it to zero, then we also manage to find what is the maximum momentum that has been absorbed by the wind turbine, and we substitute. Not substitute, sorry, we take the differentiation of this and then we get this one, and then we simply rearrange, all right, and we get this. And from the first video, we know that dm dt is equals to rho avr, right, from the previous slide, yeah. And we substitute dm dt equals to rho avr, and we get this form, all right. But remember that the maximum reductions of the linear momentum as such and the maximum reductions of the wind velocity as such is to find the maximum extractable power from the wind turbine. Therefore, we can equate that two terms together, the previous term in the previous slide and this term. Okay, the previous term is here. I am rewriting it over here, and this term together. So when we equate this term that we derive based on the reductions of the wind velocity with this term that we derive based on the reductions of the linear momentum, then we will obtain this, which solve the unknown for us of determining the values of VR. Because if you notice in this equation and in this equation, the only unknown that we do not have is VR. We have the value of V1 and V2 because that we can measure. The cross-sectional area, A represents the cross-sectional area of the wind turbine. Rho is the air density at standard atmospheric condition, and those we have as well. So the only thing that we do not have is VR. And by equating this to this, then we are able to find the values of VR, which is equals to us, which is given to us by V1 plus V2 over 2, or rather a relationship that we can use to find the value of VR. And this is a very powerful relationship, although it looks simple. Right. So let's get back to the power extractable from the wind turbine equation, which is this half rho AVR V1 square minus V2 square. And since that now we know VR is equals to V1 plus V2 over 2, we can go ahead and substitute this into here. As we substitute into here, then we will obtain this form. It will be expanded into this slightly more sophisticated form. And then we can go ahead and rearrange the equations and simplify it further to become this form, and then become finally this form. All right. And then there is a conclusion that we can draw from it. If you notice, right, the value, okay, this is the equation that we derived just now. The value of wind velocity ratio V2 over V1, okay, these two terms, yeah, V2 over V1, that results in maximum power transfer is calculated by differentiating the PEX, which is the extractable power from the wind turbine, with respect to V2 over V1 and equating to 0. Makes sense? So now the whole purpose of this passage is to say that we have derived this equation. Now I want to know what is the value of V2 over V1, or the value of the ratio between V2 and V1 that can give me the maximum extractable power. So to know maximum value, we know from our differentiation concept is that we perform differentiation against the other elements that we want to know and equate it to 0. In this case, it is V2 over V1. So you take the differentiations of PEX over V2 over V1 and equate to 0. And then you solve the equation. And from that, we realize that this results in a quadratic equation showing that the maximum PEX, the ratio of V2 over V1, must have the value of either 1 over 3 or -1. And of course, -1 doesn't make sense, and we can just ignore it. And therefore, we conclude that to get the maximum extractable power, PEX, V2 over V1 must equals to 1 over 3, or the ratio of V2 over V1 must equals to 1 to 3. So the incoming wind speed must be 3